This is lecture 20, chapter 6. In this chapter, we'll be discussing trusses, frames, and machines. And as I mentioned earlier, this would be probably one of our longer chapters that we'll cover because there's a lot of material in it. Fortunately, there's nothing really new in terms of analysis. In this chapter, we're going to continue summing forces and summing moments. And for the most part, we're going to be dealing with 2D structures. We won't deal with 3D trusses or machines for that matter. So what exactly is this chapter about? Well, up until this point, we've, especially if we look at back at chapter 4, we would look at a structure, for example, structure A here, and perhaps we would be given the weight and we would have to calculate GD. So if we go back as early as chapter 2, we would find GD assuming that A had no reaction or anything and that it was perfectly balanced by the weight. Then in chapter 4, we learned that A could be a reaction. Now in this case, A is a pin, but we learned that A could have just as well been a telephone pole or something that was embedded in the concrete, in which case it would have had a reaction moment also. So you could have been given GD and the weight, and then you could have found how much reaction was supported at A. So what we're doing now is we're looking at the same type of structure, except we're taking it apart. So figure B in this case is what we would have looked at in chapter 4. We would have identified all the external forces relative to the structure. However, if we go on to C, which is really what this chapter is about, is now we take that apart. And you'll notice that when we take it apart, the forces at each of the points, for example, at B and E, you notice that they're equal and opposite. And so that way, when you take them or put the whole thing back together again, those internal forces add to 0 because we can't have a net force internally or the thing would be moving. So we have 3 main ideas or 3 main types of problems we'll solve in this chapter. First are trusses. That's what we'll start off with. And trusses, I'm sure you've seen, roof truss is a good example. Anything where you have a structure consisting of 2 force members. And the advantage of this is that because everything's a 2 force member, we don't have to deal with any residual couples on any of our structures. So all we're going to have are forces in the direction of the individual members, making the calculations much simpler. Then after that, we'll talk about frames. Frames are similar to trusses, but except that in this case, they'll consist of members just like trusses, except now we'll add multi-force members to them. So as you remember, a multi-force member is something that's pinned, but then has an externally applied force to it. So in that case, the calculations are a little more involved, but still, again, completely manageable. And then lastly, we'll look at machines. And for the most part, when we talk about machines, we talk about things that can transmit and modify forces. So hand tools are a good example, bolt cutters, diagonal cutters, pliers, etc. And also in machines, you're going to have at least 1 multi-force member. But what you'll find is once you understand trusses and frames, machines really don't add anything new to the equation. Now, thinking about simple trusses, we have, as I said, we're going to stick to a 2-dimensional structure, and that's really what a truss is. If you look at a roof truss on a house, that each individual truss member that looks like a A-frame, its strength lies in the plane that it's in. So laterally, if you push from the side of the truss, it doesn't have strength. And so the strength comes from it in plane. And so you give it strength by adding cross members that actually support the multiple trusses together. Now that's beyond the scope of this class, and that gets more into an architectural engineering type of class. But so what we're going to worry about is just strictly looking at the in-plane forces. And so we're going to deal strictly with 2-dimensional trusses. And what we'll find is that each member of the truss is either going to be in tension or compression. And because it's a 2-force member, that direction of the force is going to be along the direction of the member. And we'll start out with simple trusses, and there's other trusses that are not simple. Now, we define a simple truss, and this is talked about more in your book, so you can read about that. But essentially, a simple truss is a truss made completely of triangles. So, for example, if we were to draw a triangle, like in picture ABC, part B in this case, if we were to add two more lines, one at B and one at C, and connect them to a third point, we would effectively be adding two more members, but we'd be adding a completely new triangle to it. And so there's another sketch in your book that'll explain that if you can't visualize it in your head. But a simple truss is essentially just a series of added triangles, and there's a very simple equation that you can use to determine what a simple truss is. I generally don't test you on that because that's something more if you were designing trusses. I'm mainly interested in your inability to calculate the individual stresses in the members. In picture A, you could see that by not having a triangle structure, but this trapezoid structure, that it's not stable, that if you apply a force to B, that it's going to collapse and change shape. And the assumption is that the joints themselves aren't very strong. We can't assume that the joint is going to hold appreciable amount of force. All the strength comes along the direction of the individual members. Here are a few types of trusses that were listed in your book. And so each of these can be solved using the same methods that I'll show you. It's just a matter of how complex they get and how many different steps you have to go through. But of course, the method's the same in all of these trusses. They're all two force members. And what we'll find out in the next lecture is this concept of a zero force member. And sometimes in trusses, there are members that aren't active. They don't actually support any force, in which case you don't have to calculate them because you can visually see that they're actually not active. And so we'll talk about that in the next one. So now I'd like to look at some examples of how you'd solve trusses. Before that, there is a method that you use to solve trusses, and there's actually two methods that we're going to learn. The first is called the method of joints. The second is actually called the method of sections. But once you understand method of joints, method of sections actually shows you, it's kind of a shortcut. But method of joints is, as the name says, is that the way you solve is you start off at one joint and you work your way through the entire truss. Now in this simple one that's pictured here, we have A, B, C, D. You would start off at either A or B. And the reason you do that is because if you know the load P, then you can determine the reaction at A and the reaction at B. Now, there is something that to be said about these reactions, and let me go ahead and we'll come back to this. And let me mention that briefly. Now, when it comes to reactions, as you'll notice in the book, is let's just draw a simple triangle truss because we're not going to really do anything. So here's our truss, and let's say it looks like this and that, and maybe even that and that. All right. So in this type of truss, you'll have a load up here. And usually loads are vertical, but they don't have to be. So whatever, there's certain value, we'll just call that Q, P, and S. So there's three loads. Now, generally the truss will be then anchored at this point here and this point here. Now, one of the things that we'll notice is that when we anchor, if we anchor with this type of anchor that looks like that, it's like a two-dimensional ball and socket, that if we call this point A, and let's just call this point, let's call it point Z, and what we would find is that this would actually have two reactions to it. It would have your A vertical, AY, and it'd have AX. This would also have Z in the X, and it'd have Z in the Y. And so in this type of situation, because the forces are vertical, then it's not that big a deal because we can see that both ZX and AX are going to be 0 because there's no horizontal forces. Now, if we want to calculate the amount of AY and how much of ZY, if this case, let's assume that in this truss that these are all equally spaced, let's say that's 3, 3, 3, and 3, whatever unit, and let's say that these forces are all equal. If that's the case, then this is symmetrical. Then we can just basically say that Q plus P plus S, let's say they all equaled 4 kilonewtons. If that was the case, then we'd have 12 kilonewtons going down, and we'd have 2 reaction points here. That means that each of these, ZY and AY, would have to equal 6 kilonewtons. Now, imagine though, and that we can see that just from this. Now, another way is, even if this wasn't proportional, as long as you know this, this, and this, these loads up here, you could sum the moments about A. And if you did that, then AX, AY, and ZX would all drop out, and then you could solve for ZY. So what you'll find on trusses, especially those that say they're heavily loaded on one side or the other, that most of the load will actually exist on one side's reaction. But you could easily solve for them with these constraints. Now let's imagine that for whatever reason we have a horizontal force applied here. We'll call that force R. Whatever the magnitude, it really doesn't matter, because in this configuration, it turns out that all we can say if we sum the forces in the X to 0 is that R plus AX plus ZX equals 0. But we don't know, we can't figure out this or this. We have no tools to do that with. Summing moments won't help us. So this is called constrained, or it's over constrained. And when it's over constrained, it means that we can't solve, there's too many variables and not enough equations. We can't solve it using the conventional techniques that we've learned. Now, when you take C204, you'll learn to incorporate the idea of yielding and, not yielding, I'm sorry, of elastic modulus and strain below yielding to do some of these calculations, but for now we can't do them. So what we do instead is, when we have our truss, is we make one of these sides, instead of having this anchor, we get rid of it and we put wheels on it. Now, if we put wheels on it, what that does is now we still have ZY, but we no longer have the ZX. So if that's the case, if there is a horizontal force without the ZX, now we can solve for AX. Now so in that situation, without this, it's now properly constrained, and so we're fine. Now, if you take it to the next extreme, where let's say you put rollers here, then that would not be over constrained, but that would be improperly constrained. Because what would happen then, it would just roll away, right? If you had rollers and rollers, it'd be nothing holding it, and you apply R, it'd accelerate. We don't do that in this class, okay? So that gives you a little idea of why every truss you see will have one side will have a normal XY, and the other side won't have that. So I just want to show you that. Back to this. All right. So again, when we work our truss, we're gonna find these reactions, and then we're going to essentially work our way through. Now, one of the things we'll notice is that in this corner here, since we're dealing with triangles, is that this corner here forms a triangle and actually forms a force triangle. So when you think about it, you have AC and AD, and then whatever this reaction is. And so if this is a vertical reaction here, because oftentimes we don't have any X component, then we can form a nice force triangle, and the forces in both AD and AC are going to essentially be proportional to the angle of AC. And I'll show that in the example. And then once you find that, you just work through the whole thing. And so this is an example of how you would do this in the first one. If you knew joint A, and in joint A, the corner, you knew the reaction there, you just create a force triangle like that. The only other types of force triangles we really do, and again, because you can only have 3 forces, this one here isn't as common. This one is common because, again, you have an easy right triangle. But the other ones we'll do are these when you have orthogonal forces. And so it's real easy to see that if you have a force connected at 4 points and they're all 90 degrees of each other, then whatever the force in dA is has to be the same as in dB because there's no other x component. Same with whatever the value of P is has to be the value of DC. Okay, so let's look at this simple example here. And in this example, we just want to find the forces in AC, AB, and CB. And actually, this is the first example in the example worksheet that is posted on Polylearn under the lecture. So hopefully you've downloaded it. If not, go ahead and take a moment, pause it, grab that thing, and then come back. So here we are. There's our diagram. Now, I didn't draw, I went kind of quick with this, but it turns out that for the distances, and let me go ahead, actually, I want to go back and get those distances. And so what we notice is 48. All right, so sorry about that. So now we have the distance. We know it's 15 inches, 48, and 20. Now, so what we can see from this is 15, 20 divided by 5. That means 3, 4, and 5 for the hypotenuse. So this angle here between C and A is a right triangle. This one over here, not quite as easy to see, but you have, in this case, you have 48 and 20. So if you divide this by 4, you get 12. You divide that by 4, you get 5. So this is a 5, 12, 13 triangle here. And look for those because the triple triangles are used quite often in the examples in this textbook. Now, we notice too is that C, if you remember from the picture, it had rollers here. So it only has a vertical reaction. AX and AY, though, had a typical triangle ball and socket type reaction. So they do have an AX. However, there's only this one 300-pound load applied. So if we only have the 300-pound load, then we can safely say that that goes to 0 and just write AX equals 0. So from inspection, AX equals 0, and we have our 3, 4, 5, and 5, 12, 13. Now, whether you write this or not is really up to you. It's more just for making sure you keep everything straight. So then we have, so we're trying to find AB, AC, and BC. So first thing we should try to figure out are what are the reactions. We know that there's 300 going down. So an easy way to find it would be to sum the moments about A, because we know that 300 times this distance is going to have to equal C times this distance. Or if we write it out, sum of the moments about A to 0, we get C times 15 minus 300 pounds times 63 equals 0. That's just 48 plus 15. So solve, we get C equals 1260 pounds. That's going up. So if this equals 1260, and we can by inspection see that AY is going to be pointing down because that's the equilibrium. So AY is going to be down and it's going to be 960. So therefore, AY equals 960 pounds. Now, if on your free body diagram in your homework or in test, you don't have to change it. I'm just doing this to show you, but just leave it how you have it because you've indicated it down here that where the direction is. Now, if we look at, again, the first thing started a joint. So we pick a joint. So we're going to start at joint A. We know the reaction there. So we know that joint A looks something like this. It has a downward force, it has a force going that way, and it has a force going that way. Now, remember that these members are either in tension or compression. So if they're in compression, they point toward the member, or I'm sorry, towards the joint. If they're in tension, they point away from it. So let's think about this configuration. We have this 960 pounds coming down. This only has an X component. So if this is going to be in equilibrium, this is going to have to be pointing that way, because then it gives us a vertical component to oppose that 960. So we know right away then that this AC here is going to be in compression. And if that's pointing that way, then that means it's going to the left in the X. That means this is going to have to go to the right. So we know then that AB is going to be in tension. And after you do a few of these, you'll see this pattern, and then you'll just know automatically based on the configuration. Now, we can create a force triangle here using AC, in which case what we could do is we could say, we could draw AB going that way. We can draw 960, which is A, going down, and then we can draw AC going back that way. Now, from our triangle, we know that the this is the 4 side of the triangle, and we know this is the 3 side of the triangle, and we know this is the 5 side of the triangle. So we could then say 960 is to 4 as, and this is just how you do any triangle. This is just taking the proportionality of the sides. So this is a 3, by the way, sorry. And so you'd say 960 is to 4 as AB is to 3 as AC is to 5. So that leads us to saying 960 divided by 4 times 5 equals AC. And if we do that, we get AC equal to 1,200 pounds. All right. If we do the same thing with AB, it's 960 divided by 4 times 3, then we get our AB equal to 720 pounds. All right. So a nice, easy way to do it. But let's say you didn't start out that way, because I know that's a little different. But I would highly encourage you to use this method, because it's much quicker, especially on final or a quiz. But let's say we did it the other way with just summing the forces. If we sum the forces in the y to 0, what are we going to have? We're going to have 4/5 AC, because again, we're just taking the proportion of the triangle, 4 over 5, right? So 4 over 5 AC, and that's in the y direction. And we've already established it's going up, so it's positive. And that's going to be minus 960, and that equals 0. So notice this is really the same thing, because what did I do? I multiply 960 by 5 force. So AC equals 5 force times 960. And what do we have here? 5 force times 960 equals AC. So the same thing, we get to 1,200 pounds. All right. So we can then go ahead, we've established that we're happy that that works. So now we know this and this, so we just have to find this. So in that case, if we go over to joint B, in joint B, what do we know? Well, if we draw B, and if this helps you, we know there's a force going down, that's 300. We know that this is going this way, and that's going that way. Since that's going down, we know that has to go up, therefore that has to go left. Now, we already know that that's tension, right? We learned that up here, that this was tension. So you might ask, okay, well, why is this pointing away if it's pointing away on the other end? Well, let's first solve and then we'll come back to that concept. So we know it's going away. So 300 there. So we know that this going away of value we've already established is AB is 720. So in our triangle, we know that this is a 5, 12, 13. 5, 12. So we know that this part here is going to be the hypotenuse. So we can then say, let me label this. This side is BC, this side is AB. So in that case, AB, if this is a 512, then it would be AB divided by 12, right? So let me draw the triangle, make it easier. So that's what the triangle would look like, proportion-wise. So AB is to 12, as BC is to 13, as 300 pounds is to 5. So that's 60 times 13. So 60 times 13 gives us a value of 7. I'm sorry, we already have that one. So no, we don't. So BC 60 times 13, that gives us, it gives us 780 pounds. All right. So we get BC equal to 780 pounds. And we guessed the direction had to be compression. So we could have also done it by just saying some of the forces in the X were 0, because we already had everything in the X since the 300 pounds is vertical. In that case, it would have just been 12/13 BC minus AB equals 0. And since we knew AB was what? 720. So, I'm sorry, AB was, 720. So that would have been 720 times 13/12. Which gave us, this here. Okay, so that was a fairly simple example. Now, if we were to look at our diagram, then the way to think about with compression and tension is that if it's compression here, it has to be compression there. And if it's compression there, it goes like that. If that's tension, just like that. Because these have to always be equal and opposite. They can't point the same direction. I think an easy example of this, if you're if you're thinking about it, if you take this pencil and I push it together, I'm compressing it. So as I'm compressing the pencil, my hand is effectively, the pencil is pushing into each end of my hand. And so the compression is both going out like this, right? So if you think about the pencil as this member here, if I'm pushing in on this member, the pencil is pushing out into my hands. With tension, if up here, if I had that, if I say if I glued the pencil to my hand and I tried to pull it apart, what would happen is it pull my skin away, but effectively you'd be trying to pull this thing apart, and so it would pull the skin on either end. So if that helps you understand the concept, but sometimes people think they should be the same on both sides. So if it's pointing that way, it should also point that way. But if you do that, you're going to get real confused and your answers aren't going to come out correctly. Okay. So now I want to do a little more complicated example. This one will take a little bit more time. And what you'll find with these is that it's a little bit more algebra involved in some of these, and that it's not as though it's not the difficulty of the concept, but just keeping everything straight. I think that can frustrate people, and especially on a test or a quiz, if you're not doing good bookkeeping with your numbers, it's real easy to make a silly math mistake that will propagate through your entire problem. So here we have an example out of your book. And this is, again, also on the worksheet. And in this case, you have Symmetrical forces, again, we'll deal symmetrical forces on this one. So we want to find the force in every member. Now, at first that looks intimidating, but because it's symmetrical, you can see that the force, whatever force we find in AB and AC, is going to be the same as in FG and EG, respectively. So in this kind of a truss, we only really have to solve the left or the right side because it's going to be the same on the other side. The other thing you'll notice is that on the worksheet that I provided is that there's a table at the bottom, and I generally will do that on quizzes or on exams. So the table will essentially have the name of the member and then two columns, one for the force in whatever units you're going to use. In this case, it'll be kilonewtons. And then either you'll say T or C for tension or compression. And if you find in one of your examples that you have zero force member, so it's zero, then there obviously isn't a T or a C. But it makes it a little easier to just put the numbers where they need to be, especially for grading on my end. Okay, so let's look at this one. So we have, you'll notice that it's 9 meters wide, and then it's divided in three pieces on the bottom and 4 pieces on the top with the respective loads. And it's 2 meters tall. So here's that same drawing. 3, 3, 3, 2.25, 2.25, and so forth. So all forces kilonewtons, and distance, we'll say, is in meters. So we'll leave that. So we want to find all members. So as I explained before, is that we could sum the moments about A, and we could solve for GY. So if we did that, we would say sum the moments about A to 0. And oh, one thing too, going back to this, sorry, before I jump ahead, notice the roller on the one side. So you see that there's a roller on this side and a normal one on that side. So as a result, we only have the reaction here and here, and then one here. Now again, AX is going to be 0 because there's no horizontal force. That makes things good. And so now we just need to solve for our MA, our AY, and our GY. Now we could solve the sum of the moments about A, in which case we'd have 3 kilonewtons times 2.25 plus 3 kilonewtons times 4.5 plus 3 kilonewtons times 6.75 plus 1.5 times 9. And then all of that would equal GY times 9. Or because it's proportional, we see that there's 3, 6, 9, 12. So we know that AY equals 6 and GY equals 6. And so what I'm going to do for my G, I probably won't draw it again, but I'm going to draw it with a lowercase because my G's tend to look like 6. So to avoid confusion, I'll do that. So notice how 6, 6 looks identical. So let's go ahead and solve this now. So we're going to look first at joint A. So joint A looks something like this. So here's joint A. All right, so I'm just drawing it like that. Now, what we know about joint A is, for one, in terms of proportions of the triangle, if we draw a straight line down from B here, we know that I didn't draw it on here, but that's 1 meter. So this would be 1, and then this bottom part would be 2.25, and therefore the hypotenuse would be 2.462. So unfortunately, it's not a nice simple triangle, but that's okay. So now we can do the proportions, though, like we did before, to find this. Now we know that's 6. So really the net force going up is going to be 6 minus the 1.5 that's here. So that's going to be 4.5 here. So what we'll do is we'll say 4.5 is to 1, because that's that side triangle. And this side, of course, is AC, this is AB. And that equals AB over 2.462. And that equals AC over 2.25. From there, we get AB equals 11.08 in compression, and AC equals 10.13. And again, these are all in kilonewtons, so I'm not going to write units. And that's tension. Now, how did I know that again? Because we know that if this force is going up, this force has to go down. If that's going to the left, this has to go to the right. So now I have those. I'm done. And so I have a choice. I can go to joint B or I can go to joint C. Now, if you think we go to joint B, we know this one. So then we're going to be solving for this and this. If we go to joint C, we have 1, 2, 3 unknowns and only 1 known. So we're not going to be able to go to joint C yet. We're going to have to go to B first, because if we go to C, we're going to have too many unknowns to solve, because again, we only have 2 equations, sum of the force in the X, sum of the forces in the Y. We're not going to do any moments at this point. So we go up to joint B. So what I'd recommend is say joint B on your paper, and go ahead and draw it as you think it should look. And so if that's my point there, I know it's going to be 3 kilonewtons coming down. And actually, I'm just going to draw 3 there, make it easier. I know that's AB. Now I already determined it's in compression, so I'm going to draw it like that. This is BD here, and we have BC here. Okay. Now at this point, I know AB is in compression. I really don't know what these are. So I can guess. It really doesn't matter, because if I guess and I'm wrong, my answer is going to be negative. That'll tell me that I guessed wrong. So I'm going to assume in this case that BC is in compression and that BD is in tension. That's just my guess. So I know that AB and BD have the same angle. So we're still dealing with a 2.25, 2.4621 triangle for AB. The other triangle, that BC, turns out, if we draw it, it looks like this. And it turns out that this is going to be a 1.75, 1.25. But if we divide that by 5, each of them, what do we get? We get a 3, 4, 5 triangle, which is easier to use. So we'll deal with the 3, 4, 5 triangle. So that's our BC here. So this is a lot easier, I find, than determining the angle. So for example, I could find that angle there, right, theta, by taking the inverse tangent of 1 over 2.25. And then I'd get the angle. And then what would I do when I came back to sum the forces in the X? Well, what would I want to know? I'd want to know how much force is in this direction. So I'd multiply my force AB times cosine theta. Well, if I multiply by cosine theta, that's the exact same number as if I just take the ratio of 2.25 over 2.462. If you don't believe me, try it. So I find in trusses that I never use angles unless they're given to me initially, and I find it's much easier to just deal with the proportions. So now let's go ahead and solve this one. So first thing, we're going to sum the forces in the X to 0. So if we sum the forces to the X in 0, we get 2.25. And actually, I'm just going to write this down really. Actually, I'll just write it while you're listening. So we're going to write down 2.25 is to 2.462 times AB. I'm not going to put in the value for AB just yet. So what that's saying is that the x component of AB is this ratio of triangle, 2.25 over 2.462. Then I'm going to add to that 2.25 over 2.462 of BD, because that's also in the same direction. And then that's going to be minus 3/5 BC. And all that is equal to 0. That's my equation 1, right? The 3/5 coming from the 3, 4, 5 triangle, and it's going this way. So now I'm going to sum the forces in the y. In that case, I get 1 over 2.462 AB plus 1 over 2.462 BD plus 4/5 BC minus 3 equals 0. So now I have this second equation. Now I have two equations and two unknowns because I know what AB is. Now this is kind of ugly because to solve this I'd have to rearrange things, and you could, but I find that with some of the equations, especially on trusses, you look at commonality. Now if I multiply this equation through by 2.25, because this is 1, and I make it a negative, I'm going to be able to get rid of one of these terms. So if I do that, I end up with multiply by negative 2.25. I end up with negative 2.25 over 2.462 AB minus 2.25 over 2.462 BD minus 9/5 BC plus, because it's negative times a negative, 6.75, all equals 0. I'm going to call it my equation 2. So I'm going to bring equation 1 down, and if I do that, I have 2.25 over 2.462 AB plus 2.25 over 2.462 BD, and then minus 3/5 BC equals 0. So notice that if I add these two drop out, these two drop out, I end up with negative 12/5 BC plus 6.75 equals 0. So move 6.7 to the other side, solve, I get BC equal to 2.813. So 2.813. And because it came out positive means I guessed the right direction, that BC is indeed in compression. So once I have that 2.813, then all you have to do is take that value and plug it back into either one of these equations and then solve for your respective BD. Now you're going to put in AB, which you already know, and you'll solve for BD. And if we do that, I'll leave you to do that. BD gives us a value of negative 9.23 kilonewtons. Now, so because when I plug, this is numbers pretty small here, 2.813. So if I plug it, let's say I plugged it back in here, I have this times, if I plug in the number here, this is going to be 11.08. So 11.8 is pretty big. And then this times 2.813 is going to be negative. So in order for this to go to 0, this is going to have to be a negative number. So that's why my resulting BD was negative. So that just means that my original assumption that it was in tension was wrong. That BD is still has the same magnitude, 9.239. The only difference is now it's in compression, and I get rid of that negative because I want it to be the correct direction that's positive, and I just named the direction with this. Now, if I had done this the opposite way, and let's say I had solved for BD by multiplying through by something different, and this had come out negative as it did, when I plug this back into these equations algebraically, I want to be sure I plug in the negative number back into the equation. If I plug in a negative number here and I get a positive number for my other answer, that means that answer was the correct assumption. Never change this and then plug it back in. You'll get screwed up with the negative signs. Okay. So we're almost there actually, because the only thing, because of the proportional aspect of the triangle, we have this, this, and this. So if we come down to joint C, we'll solve for this and this. And then because of symmetry, we'll already have these other ones. So let's go ahead and do that. And if we draw it, it looks like this, where we have CD and BC. Now BC is in compression, we know that. We know AC is in tension. And so there's CE, there's CD. We don't know. I'm going to assume that they're both in tension. I don't know, but I'm going to assume that. I also, if you calculate, even though it doesn't look like it on the diagram, but if you look at the proportions, CD is also a 3, 4, 5 triangle of the same ilk, I should say. So this looks like this. This is a 3, 4. This is also a 3, 4. So they're the same. So that tells you something right there, because if these have the same proportions, then if this BC is equal to 2.813, then in terms of Y, if we sum the forces in the Y, what do we find? Well, if we sum the forces in the Y to 0, then we know that we have 4/5 CD, because that's the horizontal version, minus 4/5 BC equals 0. So essentially they're the same. So therefore CD equals 2.813, and it's also in tension because I guessed correctly. So lastly, this is nice because I could solve directly for it, means I'm not going to have two equations, two unknowns. I'm just going to be able to solve directly. So we go ahead and sum the forces in the X to 0, and we get CE minus AC plus 3/5 BC plus 3/5 CD. So in this case, all we have to do then is plug in, because we know that CE is just going to equal to 10.13. So I moved it to the other side of the, oh wait, I'm sorry, this equals 0. So that, I move this to the other side, and that's going to be minus 3/5 times 2.813 minus 3/5 times 2.813. Therefore, CE is 6.75 in tension. And there you have it. So that's how you solve those. That one, again, was a little easier because we didn't have to deal with the fact that we had different loading on different sides. And so we had proportion on one side, and we could just put those values on the other. So that does it for this lecture. So this was lecture 20. So lecture 21, we're going to talk about zero force members and probably do another example, including zero force members. And then in lecture 22, we'll talk about method of sections. So thank you, and stay safe.